Galaxy universe defined. A galaxy is a system of stars, stellar remnants, interstellar gas, dust, dark matter bound together by gravity. The word is derived from the Greek galaxies, literally milky, a reference to the Milky Way galaxy that contains the solar system. Galaxies, averaging an estimated 100 million stars, range in size from dwarfs with less than 100 million stars to the largest galaxies, known supergiants, with 100 trillion stars, each orbiting its galaxy's center of mass. Most of the mass in a typical galaxy is in the form of dark matter, with only a few % of that mass visible in the form of stars and nebulae. Supermassive black holes are a common feature at the centers of galaxies. Galaxies are categorized according to their visual morphology as elliptical, spiral, or irregular. Many are thought to have supermassive black holes at their centers. The Milky Way's central black hole, known as Sagittarius at asterisk, has a mass 4 million times greater than the Sun. As of March 2016, GN-Zelevin is the oldest and most distant galaxy observed. It has a moving distance of 32 billion light-years from Earth and is seen as it existed just 400 million years after the Big Bang. In 2016, using 20 years of images from the Hubble Space Telescope, it was estimated that there were in total 2,021,012 or more galaxies in the observable universe, and as many as an estimated 11,024 stars, more stars than all the grains of sand on all beaches of the planet Earth. In 2021, data from NASA's New Horizons space probe was used to revise the earlier estimate to roughly 200 billion galaxies, 21,011. Most galaxies are 1,000 to 100,000 parsecs in diameter, approximately 3,000 to 300,000 light-years, and are separated by distances on the order of millions of parsecs or megapart. For comparison, the Milky Way has a diameter of at least 26,800 parsecs, 87,400 Li, and is separated from the Andromeda Galaxy with diameter of about 152,000 Li, its nearest large neighbor, by 780,000 parsecs, 2.5 million Li. The space between galaxies is filled with a tenuous gas, the intergalactic medium, with an average density of less than 1 atom per cubic meter. Most galaxies are gravitationally organized into groups, clusters, and superclusters. The Milky Way is part of the local group, which it dominates along with Andromeda Galaxy. The group is part of the Virgo supercluster. At the largest scale, these associations are generally arranged into sheets and filaments surrounded by immense voids. Both the local group and the Virgo supercluster are contained in a much larger cosmic structure named Laniakea. Etymology. The word galaxy was borrowed via French and medieval Latin from the Greek term for the Milky Way, Galaxias kaklos gamma alpha lambda alpha psi iota alpha sigma kappa epsilon kappa lambda omicron sigma, Milky Circle, named after its appearance as a milky band of light in the sky. In Greek mythology, Zeus places his son born by a mortal woman, the infant Heracles, on Hera's breast while she is asleep, so the baby will drink her divine milk and thus become immortal. Hera wakes up while breastfeeding and then realizes she is nursing an unknown baby. She pushes the baby away, some of her milk spills, and it produces the band of light known as the Milky Way. In the astronomical literature, the capitalized word galaxy is often used to refer to the Milky Way galaxy to distinguish it from the other galaxies in the observable universe. The English term Milky Way can be traced back to a story by Chaucer c. 1380. See yonder, lo, the galaxia which men cleepeth the Milky Way, for hit his wit. Galaxies were initially discovered telescopically and were known as spiral nebulae. Most 18th to 19th century astronomers considered them as either unresolved star clusters or anagalactic nebulae, and were just thought of as a part of the Milky Way, but their true composition and natures remained a mystery. Observations using larger telescopes of a few nearby bright galaxies, like the Andromeda Galaxy, began resolving them into huge conglomerations of stars, but based simply on the apparent faintness and sheer population of stars. The true distances of these objects placed them well beyond the Milky Way. For this reason they were popularly called island universes, but this term quickly fell into disuse, as the word universe implied the entirety of existence. Instead, they became known simply as galaxies. Nomenclature. Tens of thousands of galaxies have been catalogued, but only a few have well-established names, such as the Andromeda Galaxy, the Magellanic Clouds, the Whirlpool Galaxy, and the Sombrero Galaxy. Astronomers work with numbers from certain catalogues such as the Messier Catalogue, the NJC New General Catalogue, the IC Index Catalogue, the CGCG Catalogue of Galaxies and of Clusters of Galaxies, the MCG Morphological Catalogue of Galaxies, the UGC Uppsala General Catalogue of Galaxies, and the PGC Catalogue of Principal Galaxies, also known as LEDA. All the well-known galaxies appear in one or more of these catalogues, but each time under a different number. For example, Messier 109 or Mon 109 is a spiral galaxy having the number 109 in the catalogue of Messier. It also has the designations NGC 3992, UGC 6930, CGCG 216 9-23, and CG plus 9-20-44, and PGC 37617 or LEDA 37617. Millions of fainter galaxies are known by their identifiers in sky surveys such as the Sloan Digital Sky Survey, in which Mon 109 is catalogued as SDS as Joan 115,735.97 plus 532,228.9. Observation history. The realization that we live in a galaxy that is one among many parallels, major discoveries about the Milky Way and other nebulae. Milky Way, Greek, philosopher Democritus, 450–370 BC, proposed that the bright band on the night sky known as the Milky Way might consist of distant stars. Aristotle, 384–322 BCE, however, believed the Milky Way was caused by the ignition of the fiery exhalation of some stars that were large, numerous, and close together, and that the ignition takes place in the upper part of the atmosphere, in the region of the world that is continuous with the heavenly motions. Neoplatonist philosopher Olympiodorus the Younger c. 495–570 CE was critical of this view, arguing that if the Milky Way was sublunarily situated between Earth and the Moon it should appear different at different times and places on Earth, and that it should have parallax, which it did not. In his view, the Milky Way was celestial. According to Mohani Mohammed, Arabian astronomer Alhazen 960–5–1037 made the first attempt at observing and measuring the Milky Way's parallax, and he thus determined that because the Milky Way had no parallax, it must be remote from the Earth, not belonging to the atmosphere. Persian astronomer Al-Iruni 973–1048 proposed the Milky Way galaxy was a collection of countless fragments of the nature of nebulous stars. Andalusian astronomer Ibn Bajjah Ibn Pace d. 1138 proposed that it was composed of many stars that almost touched one another and appeared to be a continuous image due to the effect of refraction from sublunary material, citing his observation of the conjunction of Jupiter and Mars as evidence of this occurring when two objects were near. In the 14th century, Syrian-born Ibn Khayyam proposed the Milky Way galaxy was a myriad of tiny stars packed together in the sphere of the fixed stars. Actual proof of the Milky Way consisting of many stars came in 1610 when the Italian astronomer Galileo Galilei used a telescope to study it and discovered it was composed of a huge number of faint stars. In 1750, English astronomer Thomas Wright, in his An Original Theory or New Hypothesis of the Universe, correctly speculated that it might be a rotating body of a huge number of stars held together by gravitational forces akin to the solar system but on a much larger scale, and that the resulting disk of stars could be seen as a band on the sky from a perspective inside it. In his 1755 treatise, Immanuel Kant elaborated on Wright's idea about the Milky Way's structure. The first project to describe the shape of the Milky Way and the position of the Sun was undertaken by William Herschel in 1785 by counting the number of stars in different regions of the sky. He produced a diagram of the shape of the galaxy with the solar system close to the center. Using a refined approach, Kapteyn in 1920 arrived at the picture of a small diameter, about 15 kiloparsecs ellipsoid galaxy with the Sun close to the center. A different method by Harlow Shapley based on the cataloguing of globular clusters led to a radically different picture, a flat disk with diameter approximately 70 kiloparsecs and the Sun far from the center. Both analyses failed to take into account the absorption of light by interstellar dust present in the galactic plane, but after Robert Julius Trumpler quantified this effect in 1930 by studying open clusters, the present picture of the Milky Way galaxy emerged. Distinction from other nebulae. A few galaxies outside the Milky Way are visible on a dark night to the unaided eye, including the Andromeda Galaxy, Large Magellanic Cloud, Small Magellanic Cloud, and the Triangulum Galaxy. In the 10th century, Persian astronomer al-Sufi made the earliest recorded identification of the Andromeda Galaxy, describing it as a small cloud. In 964, he probably mentioned the Large Magellanic Cloud in his book of Fixed Stars, referring to al-Bakr of the Southern Arabs, since at a declination of about 70 degrees south it was not visible where he lived. It was not well known to Europeans until Magellan's voyage in the 16th century. The Andromeda Galaxy was later independently noted by Simon Marius in 1612. In 1734, philosopher Emanuel Swedenborg in his Principia speculated that there might be other galaxies outside that were formed into galactic clusters that were minuscule parts of the universe that extended far beyond what could be seen. These views are remarkably close to the present-day views of the cosmos. In 1745, Pierre-Louis Maupertuis conjectured that some nebula-like objects were collections of stars with unique properties, including a glow exceeding the light its stars produced on their own, and repeated Johannes Hevelius's view that the bright spots were massive and flattened due to their rotation. In 1750, Thomas Wright correctly speculated that the Milky Way was a flattened disk of stars, and that some of the nebulae visible in the night sky might be separate Milky Ways. Toward the end of the 18th century, Charles Messier compiled a catalogue containing the 109 brightest celestial objects having nebulous appearance. Subsequently, William Herschel assembled a catalogue of 5,000 nebulae. In 1845, Lord Rosse constructed a new telescope and was able to distinguish between elliptical and spiral nebulae. He also managed to make out individual point sources in some of these nebulae, lending credence to Kant's earlier conjecture. In 1912, Vesto Slipher made spectrographic studies of the brightest spiral nebulae to determine their composition. Slipher discovered that the spiral nebulae have high Doppler shifts, indicating that they are moving at a rate exceeding the velocity of the stars he had measured. He found that the majority of these nebulae are moving away from us. In 1917, Heber Curtis observed Nova S Andromedae within the Great Andromeda Nebula as the Andromeda Galaxy, Messier object M31, was then known. Searching the photographic record, he found 11 more Navi. Curtis noticed that these Navi were, on average, 10 magnitudes fainter than those that occurred within this galaxy. As a result, he was able to come up with a distance estimate of 150,000 parsecs. He became a proponent of the so-called island universes hypothesis, which holds that spiral nebulae are actually independent galaxies. In 1920, a debate took place between Harlow Shapley and Heber Curtis, the Great Debate concerning the nature of the Milky Way, spiral nebulae, and the dimensions of the universe. To support his claim that the Great Andromeda Nebula is an external galaxy, Curtis noted the appearance of dark lanes resembling the dust clouds in the Milky Way, as well as the significant Doppler shift. In 1922, the Estonian astronomer Ernst Erpik gave a distance determination that supported the theory that the Andromeda Nebula is indeed a distant extragalactic object. Using the new 100-inch MT Wilson telescope, Edwin Hubble was able to resolve the outer parts of some spiral nebulae as collections of individual stars and identified some Cepheid variables, thus allowing him to estimate the distance to the nebulae. They were far too distant to be part of the Milky Way. In 1936, Hubble produced a classification of galactic morphology that is used to this day. Modern research. In 1944, Hendrik van de Hulst predicted that microwave radiation with wavelength of 21 cm would be detectable from interstellar atomic hydrogen gas, and in 1951 it was observed. This radiation is not affected by dust absorption, and so its Doppler shift can be used to map the motion of the gas in this galaxy. These observations led to the hypothesis of a rotating bar structure in the center of this galaxy. With improved radio telescopes, hydrogen gas could also be traced in other galaxies. In the 1970s, Vera Rubin uncovered a discrepancy between observed galactic rotation speed and that predicted by the visible mass of stars and gas. Today, the galaxy rotation problem is thought to be explained by the presence of large quantities of unseen dark matter. Beginning in the 1990s, the Hubble Space Telescope yielded improved observations. Among other things, its data helped establish that the missing dark matter in this galaxy could not consist solely of inherently faint and small stars. The Hubble Deep Field, an extremely long exposure of a relatively empty part of the sky, provided evidence that there are about 125 billion 1.25 times 1011 galaxies in the observable universe. Improved technology in detecting the spectra invisible to humans' radio telescopes, infrared cameras, and X-ray telescopes allows detection of other galaxies that are not detected by Hubble. Particularly, surveys in the zone of avoidance, the region of sky blocked at visible light wavelengths by the Milky Way, have revealed a number of new galaxies. A 2016 study published in the Astrophysical Journal, led by Christopher Consellis of the University of Nottingham, used 20 years of Hubble images to estimate that the observable universe contained at least 2 trillion 2 times 1012 galaxies. However, later observations with the New Horizons space probe from outside the zodiacal light reduced this to roughly 200 billion 2 times 1011. Types and morphology. Galaxies come in 3 main types: ellipticals, spirals, and irregulars. A slightly more extensive description of galaxy types based on their appearance is given by the Hubble sequence. Since the Hubble sequence is entirely based upon visual morphological type shape, it may miss certain important characteristics of galaxies such as star formation rate in starburst galaxies and activity in the cores of active galaxies. Ellipticals. The Hubble classification system rates elliptical galaxies on the basis of their ellipticity, ranging from S0, being nearly spherical, up to S7, which is highly elongated. These galaxies have an ellipsoidal profile, giving them an elliptical appearance regardless of the viewing angle. Their appearance shows little structure, and they typically have relatively little interstellar matter. Consequently, these galaxies also have a low portion of open clusters and a reduced rate of new star formation. Instead, They are dominated by generally older, more evolved stars that are orbiting the common center of gravity in random directions. The stars contain low abundances of heavy elements because star formation ceases after the initial burst. In this sense, they have some similarity to the much smaller globular clusters. Type C-D galaxies. The largest galaxies are the Type C-D galaxies. First described in 1964 by a paper by Thomas and Matthews and others, they are a subtype of the more general class of D galaxies, which are giant elliptical galaxies, except that they are much larger. They are popularly known as the supergiant elliptical galaxies and constitute the largest and most luminous galaxies known. These galaxies feature a central elliptical nucleus with an extensive, faint halo of stars extending to megaparsec scales. The profile of their surface brightnesses as a function of their radius or distance from their cores falls off more slowly than their smaller counterparts. The formation of these CD galaxies remains an active area of research, but the leading model is that they are the result of the mergers of smaller galaxies in the environments of dense clusters, or even those outside of clusters with random overdensities. These processes are the mechanisms that drive the formation of fossil groups or fossil clusters, where a large, relatively isolated, supergiant elliptical resides in the middle of the cluster and are surrounded by an extensive cloud of X-rays as the residue of these galactic collisions. Another older model posits the phenomenon of cooling flow, where the heated gases in clusters collapses towards their centers as they cool, forming stars in the process, a phenomenon observed in clusters such as Perseus and more recently in the Phoenix cluster. Shell galaxy. A shell galaxy is a type of elliptical galaxy where the stars in its halo are arranged in concentric shells. About 1/10 of elliptical galaxies have a shell-like structure, which has never been observed in spiral galaxies. These structures are thought to develop when a larger galaxy absorbs a smaller companion galaxy that as the two galaxy centers approach, they start to oscillate around a center point, and the oscillation creates gravitational ripples forming the shells of stars, similar to ripples spreading on water. For example, Galaxy NGC 3923 has over 20 shells. Spirals. Spiral galaxies resemble spiraling pinwheels. Though the stars and other visible material contained in such a galaxy lie mostly on a plane, the majority of mass in spiral galaxies exists in a roughly spherical halo of dark matter which extends beyond the visible component as demonstrated by the universal rotation curve concept. Spiral galaxies consist of a rotating disk of stars and interstellar medium, along with a central bulge of generally older stars. Extending outward from the bulge are relatively bright arms. In the Hubble classification scheme, spiral galaxies are listed as type S, followed by a letter a B or C, which indicates the degree of tightness of the spiral arms and the size of the central bulge. An SA galaxy has tightly wound, poorly defined arms and possesses a relatively large core region. At the other extreme, an SC galaxy has open, well-defined arms and a small core region. A galaxy with poorly defined arms is sometimes referred to as a flocculate spiral galaxy, in contrast to the grand design spiral galaxy that has prominent and well-defined spiral arms. The speed in which a galaxy rotates is thought to correlate with the flatness of the disk, as some spiral galaxies have thick bulges while others are thin and dense. In spiral galaxies, the spiral arms do have the shape of approximate logarithmic spirals, a pattern that can be theoretically shown to result from a disturbance in a uniformly rotating mass of stars. Like the stars, the spiral arms rotate around the center, but they do so with constant angular velocity. The spiral arms are thought to be areas of high-density matter, or density waves. As stars move through an arm, the space velocity of each stellar system is modified by the gravitational force of the higher density, The velocity returns to normal after the stars depart on the other side of the arm. This effect is akin to a wave of slowdowns moving along a highway full of moving cars. The arms are visible because the high density facilitates star formation, and therefore they harbor many bright and young stars. Bart's spiral galaxy. A majority of spiral galaxies, including the Milky Way galaxy, have a linear, bar-shaped band of stars that extends outward to either side of the core, then merges into the spiral arm structure. In the Hubble classification scheme, these are designated by an SB followed by a lowercase letter A, B, or C, which indicates the form of the spiral arms in the same manner as the categorization of normal spiral galaxies. Bars are thought to be temporary structures that can occur as a result of a density wave radiating outward from the core or else due to a tidal interaction with another galaxy. Many barred spiral galaxies are active, possibly as a result of gas being channeled into the core along the arms. Our own galaxy, the Milky Way, is a large disc-shaped barred spiral galaxy about 30 kiloparsecs in diameter and a kiloparsec thick. It contains about 200 billion 2 times 10^11 stars and has a total mass of about 600 billion 6 times 10^11 times the mass of the Sun. Superluminous spiral. Recently, researchers described galaxies called superluminous spirals. They are very large with an upward diameter of 437,000 light-years compared to the Milky Way's 87,400 light-year diameter. With a mass of 340 billion solar masses, they generate a significant amount of ultraviolet and mid-infrared light. They are thought to have an increased star formation rate around 30 times faster than the Milky Way. Other morphologies. Peculiar galaxies are galactic formations that develop unusual properties due to tidal interactions with other galaxies. A ring galaxy has a ring-like structure of stars and interstellar medium surrounding a bare core. A ring galaxy is thought to occur when a smaller galaxy passes through the core of a spiral galaxy. Such an event may have affected the Andromeda galaxy, as it displays a multi-ring-like structure when viewed in infrared radiation. A lenticular galaxy is an intermediate form that has properties of both elliptical and spiral galaxies. These are categorized as Hubble-type 0, and they possess ill-defined spiral arms with an elliptical halo of stars. Barred lenticular galaxies receive Hubble classification SB0. Irregular galaxies are galaxies that cannot be readily classified into an elliptical or spiral morphology. An Uri galaxy has some structure but does not align cleanly with the Hubble classification scheme. Roman II galaxies do not possess any structure that resembles a Hubble classification and may have been disrupted. Nearby examples of dwarf irregular galaxies include the Magellanic Clouds. An ultra-diffuse galaxy UDG is an extremely low-density galaxy. It may be the same size as the Milky Way, but have a visible star count only 1% of the Milky Way's. Its lack of luminosity is due to a lack of star-forming gas, resulting in old stellar populations. Dwarfs. Despite the prominence of large elliptical and spiral galaxies, most galaxies are dwarf galaxies. They are relatively small when compared with other galactic formations, being about 100th the size of the Milky Way, with only a few billion stars. Ultra-compact dwarf galaxies have recently been discovered that are only 100 parsecs across. Many dwarf galaxies may orbit a single larger galaxy. The Milky Way has at least a dozen such satellites, with an estimated 300-500 yet to be discovered. Dwarf galaxies may also be classified as elliptical, spiral, or irregular. Since small dwarf ellipticals bear little resemblance to large ellipticals, they are often called dwarf spheroidal galaxies instead. A study of 27 Milky Way neighbors found that in all dwarf galaxies the central mass is approximately 10 million solar masses, regardless of whether it has thousands or millions of stars. This suggests that galaxies are largely formed by dark matter, and that the minimum size may indicate a form of warm dark matter incapable of gravitational coalescence on a smaller scale. Other types of galaxies. Interacting. Interactions between galaxies are relatively frequent, and they can play an important role in galactic evolution. Near misses between galaxies result in warping distortions due to tidal interactions and may cause some exchange of gas and dust. Collisions occur when two galaxies pass directly through each other and have sufficient relative momentum not to merge. The stars of interacting galaxies usually do not collide, but the gas and dust within the two forms interacts, sometimes triggering star formation. A collision can severely distort the galaxy's shapes, forming bars, rings, or tail-like structures. At the extreme of interactions are galactic mergers, where the galaxy's relative momentums are insufficient to allow them to pass through each other. Instead, they gradually merge to form a single, larger galaxy. Mergers can result in significant changes to the galaxy's original morphology. If one of the galaxies is much more massive than the other, the result is known as cannibalism, where the more massive larger galaxy remains relatively undisturbed and the smaller one is torn apart. The Milky Way galaxy is currently in the process of cannibalizing the Sagittarius dwarf elliptical galaxy and the Canis Major dwarf galaxy. Starburst. Stars are created within galaxies from a reserve of cold gas that forms giant molecular clouds. Some galaxies have been observed to form stars at an exceptional rate, which is known as a starburst. If they continue to do so, they would consume their reserve of gas in a time span less than the galaxy's lifespan. Hence, starburst activity usually lasts only about 10 million years, a relatively brief period in a galaxy's history. Starburst galaxies were more common during the universe's early history, but still contribute an estimated 15% to total star production. Starburst galaxies are characterized by dusty concentrations of gas and the appearance of newly formed stars, including massive stars that ionize the surrounding clouds to create H-Roman II regions. These stars produce supernova explosions, creating expanding remnants that interact powerfully with the surrounding gas. These outbursts trigger a chain reaction of star building that spreads throughout the gaseous region. Only when the available gas is nearly consumed or dispersed does the activity end. Starbursts are often associated with merging or interacting galaxies. The prototype example of such a starburst forming interaction is Métis 2, which experienced a close encounter with the larger Métis 1. Irregular galaxies often exhibit spaced knots of starburst activity. Radiogalaxy. A radiogalaxy is a galaxy with giant regions of radio emission extending well beyond its visible structure. These energetic radio lobes are powered by jets from its active galactic nucleus. Radio galaxies are classified according to their Fanneroff-Riley FR classifications. The FRI class are a minority class low luminosity sources exhibiting structures usually known as plumes, which are much more elongated. The FR Roman II class are by far the most common, exhibiting large-scale structures or called lobes. These are double, often fairly symmetrical, roughly ellipsoidal structures placed on either side of the active nucleus. Radio galaxies can also be classified as giant radio galaxies GRJS, whose radio emissions can extend to scales of megaparsecs 3.26 million light-years. Alcyoneus is an FR Roman II class low-excitation radio galaxy which has the largest observed radio emission, with lobed structures spanning 5 megaparsecs 16 times 106 Li. For comparison, another similarly sized giant radio galaxy is 3C236, with lobes 15 million light-years across. It should, however, be noted that radio emissions are not always considered part of the main galaxy itself, and is usually not used as a standard in measuring the physical diameter of a galaxy. For insight on how physical diameters of galaxies are measured, see section Physical Diameters below. A giant radio galaxy is a special class of objects characterized by the presence of radial lobes generated by relativistic jets powered by the central galaxy's supermassive black hole. Giant radio galaxies are different from ordinary radio galaxies in that they can extend to much larger scales, reaching upwards to several megaparsecs across, far larger than the diameters of their host galaxies. Active galaxy. Some observable galaxies are classified as active if they contain an active galactic nucleus AGN. A significant portion of the galaxy's total energy output is emitted by the active nucleus instead of its stars, dust and interstellar medium. There are multiple classification and naming schemes for ANDs, but those in the lower ranges of luminosity are called Seyfert galaxies, while those with luminosities much greater than that of the host galaxy are known as quasi-stellar objects or quasars. AGN emit radiation throughout the electromagnetic spectrum from radio wavelengths to X-rays, though some of it may be absorbed by dust or gas associated with the AGN itself or with the host galaxy. The standard model for an active galactic nucleus is based on an accretion disk that forms around a supermassive black hole SMBH at the galaxy's core region. The radiation from an active galactic nucleus results from the gravitational energy of matter as it falls toward the black hole from the disk. The AGN luminosity depends on the SMBH's mass and the rate at which matter falls onto it. In about 10% of these galaxies, a diametrically opposed pair of energetic jets ejects particles from the galaxy core at velocities close to the speed of light. The mechanism for producing these jets is not well understood. Blazars. Blazars are believed to be active galaxies with a relativistic jet pointed in the direction of Earth. A radio galaxy emits radio frequencies from relativistic jets. A unified model of these types of active galaxies explains their differences based on the observer's position. Lynards, possibly related to active galactic nuclei as well as starburst regions, are low ionization nuclear emission line regions, LINARs. The emission from LINAR-type galaxies is dominated by weakly ionized elements. The excitation sources for the weakly ionized lines include post-AGB stars and shocks. Approximately one-third of nearby galaxies are classified as containing LINAR nuclei. Seyfert galaxy. Seyfert galaxies are one of the two largest groups of active galaxies, along with quasars. They have quasar-like nuclei, very luminous, distant, and bright sources of electromagnetic radiation with very high surface brightnesses, but unlike quasars, their host galaxies are clearly detectable. Seyfert galaxies account for about 10% of all galaxies. Seen in visible light, most look like normal spiral galaxies, but when studied under other wavelengths, their core's luminosity is equivalent to the luminosity of whole galaxies the size of the Milky Way. Quasar. Quasars /stress KWE small cap I Z alpha R / or quasi-stellar radio sources are the most energetic and distant members of active galactic nuclei. Extremely luminous, they were first identified as high redshift sources of electromagnetic energy, including radio waves and visible light, that appeared more similar to stars than to extended sources similar to galaxies. Their luminosity can be 100 times that of the Milky Way. Luminous infrared galaxy. Luminous infrared galaxies Lurgs are galaxies with luminosities, the measurement of electromagnetic power output above 1011 L. Solar luminosities. In most cases, most of their energy comes from large numbers of young stars which heat surrounding dust, which irradiates the energy in the infrared. Luminosity high enough to be a Lurg requires a star formation rate of at least 18 m, a -1. Ultraluminous infrared galaxies, ULURGs, are at least 10 times more luminous still and form stars at rates bigger than 180 m, a -1. Many Lurgs also emit radiation from an AGN. Infrared galaxies emit more energy in the infrared than all other wavelengths combined, with peak emission typically at wavelengths of 60 to 100 microns. Lurgs are uncommon in the local universe, but were much more common when the universe was younger. Physical diameters. Galaxies do not have a definite boundary by their nature, and are characterized by a gradually decreasing stellar density as a function of increasing distance from their center, making measurements of their true extents difficult. Nevertheless, astronomers over the past few decades have made several criteria in defining the sizes of galaxies. As early as the time of Edwin Hubble in 1936, there have been attempts to characterize the diameters of galaxies. With the advent of large sky surveys in the second half of the 20th century, the need for a standard for accurate determination of galaxy sizes has been in greater demand due to its enormous implications in astrophysics, such as the accurate determination of the Hubble constant. Various standards have been adapted over the decades, some more preferred than others. Below are some of these examples. Isophotal diameter. The isophotal diameter is introduced as a conventional way of measuring a galaxy's size based on its apparent surface brightness. Isophotes are curves in a diagram such as a picture of a galaxy that adjoins points of equal brightnesses, and are useful in defining the extent of the galaxy. The apparent brightness flux of a galaxy is measured in units of magnitudes per square arcsecond mag/arcsecto, sometimes expressed as mag arcsec -2, which defines the brightness depth of the isophote. To illustrate how this unit works, a typical galaxy has a brightness flux of 18 mag/arcsecto at its central region. This brightness is equivalent to the light of an 18th magnitude hypothetical point object like a star being spread out evenly in a 1 square arcsecond area of the sky. For the purposes of objectivity, the spectrum of light being used is sometimes also given in figures. As an example, the Milky Way has an average surface brightness of 22.1 b mag/arcsec -2, where b mag refers to the brightness at the B band 445 nm wavelength of light in the blue part of the visible spectrum. R. O. Redman in 1936 suggested that the diameters of galaxies then referred to as elliptical nebulae should be defined at the 25.0 mag/arcsecto isophote at the B band, which is expected to cover much of the galaxy's light profile. This isophote then became known simply as D25, short for diameter 25, and corresponds to at least 10% of the normal brightness of the night sky, which is very near the limitations of blue filters at that time. This method was particularly used during the creation of the Uppsala General Catalogue using blue filters from the Palomar Observatory Sky Survey in 1972. This conventional standard, however, is not universally agreed upon. Erik Holmberg in 1958 measured the diameters of at least 300 galaxies at the isophote of about 26.5 mag/arcsecto, originally defined as where the photographic brightness density with various other surveys such that of the ESO in 1989 use isophotes as faint as 27.0 mag/arcsecto. Nevertheless, corrections of these diameters were introduced by both the second and third reference catalogue of galaxies RC2 and RC3, at least to those galaxies being covered by the two catalogues. Examples of isophotal diameter measurements Large Magellanic Cloud 9.86 kiloparsecs, 32,200 light-years at the 25.0 b mag/arcsecto isophote. Milky Way has a diameter at the 25.0 b mag/arcsecto isophote of 26.8 plus or minus 1.1 kiloparsecs, 87,400 plus or minus 3,590 light-years. Messier 87 has a diameter at the 25.0 b mag/arcsecto isophote of 40.55 kiloparsecs, 132,000 light-years. Andromeda Galaxy has a diameter at the 25.0 b mag/arcsecto isophote of 46.56 kiloparsecs, 152,000 light-years. Effective radius half-light and its variations. The half-light radius, also known as effective radius, Re, is a measure that is based on the galaxy's overall brightness flux. This is the radius upon which half, or 50%, of the total brightness flux of the galaxy was emitted. This was first proposed by Gerard de Vaucouleurs in 1948. The choice of using 50% was arbitrary but proved to be useful in further works by R. Fish in 1963, where he established a luminosity concentration law that relates the brightnesses of elliptical galaxies and their respective Re, and by J. L. Sayazik in 1968 that defined a mass-radius relation in galaxies. In defining Re, it is necessary that the overall brightness flux galaxy should be captured with a method employed by Berchetti in 2000, suggesting to measure twice the size where the brightness flux of an arbitrarily chosen radius, defined as the local flux divided by the overall average flux, equals to 0.2. Using half-light radius allows a rough estimate of a galaxy's size, but is not particularly helpful in determining its morphology. Variations of this method exist. In particular, in the ESO Uppsala Catalogue of Galaxies, values of 50%, 70%, and 90% of the total blue light, the light detected through a B-band specific filter, had been used to calculate a galaxy's diameter. Petrosian magnitude. First described by V. Petrosian in 1976, a modified version of this method has been used by the Sloan Digital Sky Survey SDSS. This method employs a mathematical model on a galaxy whose radius is determined by the azimuthally horizontal averaged profile of its brightness flux. In particular, the SDSS employed the Petrosian magnitude in the R band 658 nm in the red part of the visible spectrum to ensure that the brightness flux of a galaxy would be captured as much as possible while counteracting the effects of background noise. For a galaxy whose brightness profile is exponential, it is expected to capture all of its brightness flux, and 80% for galaxies that follow a profile under de Vaucouleurs's law. Petrosian magnitudes have the advantage that it is redshift and distance independent, allowing the measurement of the galaxy's apparent size since the Petrosian radius is defined in terms of the galaxy's overall luminous flux. A critique of an earlier version of this method has been issued by IPAC, with the method causing a magnitude of error upwards to 10% of the values than using isophotal diameter. The use of Petrosian magnitudes also have the disadvantage of missing most of the light outside the Petrosian aperture, which is defined relative to the galaxy's overall brightness profile, especially for elliptical galaxies with higher signal-to-noise ratios on higher distances and redshifts. A correction for this method has been issued by Graham et al. In 2005, based on the assumption that galaxies follow Sirzac's law. Near-infrared method. This method has been used by 2MASS as an adaptation from the previously used methods of isophotal measurement. Since 2MASS operates in the near-infrared, which has the advantage of being able to recognize dimmer, cooler, and older stars, it has a different form of approach compared to other methods that normally use B filter. The detail of the method used by 2MASS has been described thoroughly in a document by Jarrett et al., with the survey measuring several parameters. The standard aperture ellipse area of detection is defined by the infrared isophote at the Ks band roughly 2.2 μm wavelength of 20 mag/arcsecto. Gathering the overall luminous flux of the galaxy has been employed by at least 4 methods, the first being a circular aperture extending 7 arcseconds from the center, an isophote at 20 mag/arcsecto, a total aperture defined by the radial light distribution that covers the supposed extent of the galaxy, and the Prahn aperture defined as 2.5 times the first moment radius, and integration of the flux of the total aperture. Properties. Magnetic fields. Galaxies have magnetic fields of their own. They are strong enough to be dynamically important, as they drive mass inflow into the centers of galaxies, modify the formation of spiral arms, can affect the rotation of gas in the galaxy's outer regions, provide the transport of angular momentum required for the collapse of gas clouds, and hence the formation of new stars. The typical average equipartition strength for spiral galaxies is about 10 μg microgauss or 1 nt nanotesla. By comparison, the Earth's magnetic field has an average strength of about 0.3 G Gauss or 30 μt microtesla. Radio-faint galaxies like M31 and M33, the Milky Way's neighbors, have weaker fields about 5 μg, while gas-rich galaxies with high star formation rates like M51, M83, and NGC 6946 have 15 μg on average. In prominent spiral arms, the field strength can be up to 25 μg in regions where cold gas and dust are also concentrated. The strongest total equipartition fields, 50-100 μg, were found in starburst galaxies, for example, in M82 and the antennae, and in nuclear starburst regions, such as the centers of NGC 1097 and other barred galaxies. Formation and evolution. Galactic formation and evolution is an active area of research in astrophysics. Formation. Current models of the formation of galaxies in the early universe are based on the lambda-CDM model. About 300,000 years after the Big Bang, atoms of hydrogen and helium began to form in an event called recombination. Nearly all the hydrogen was neutral, non-ionized, and readily absorbed light, and no stars had yet formed. As a result, this period has been called the Dark Ages. It was from density fluctuations or anisotropic irregularities in this primordial matter that larger structures began to appear. As a result, masses of baryonic matter started to condense within cold dark matter halos. These primordial structures eventually became the galaxies we see today. Early galaxy formation. Evidence for the appearance of galaxies very early in the universe's history was found in 2006, when it was discovered that the galaxy Io-K-1 has an unusually high redshift of 6.96, corresponding to just 750 million years after the Big Bang, and making it the most distant and earliest to form galaxy seen at that time. While some scientists have claimed other objects, such as Abell 1830, Phi by R 1916, have higher redshifts and therefore are seen in an earlier stage of the universe's evolution, Io-K-1's age and composition have been more reliably established. In December 2012, astronomers reported that UD FJ-39,546,284 is the most distant object known and has a redshift value of 11.9. The object, estimated to have existed around 380 million years after the Big Bang, which was about 13.8 billion years ago, is about 13.42 billion light travel distance years away. The existence of galaxies so soon after the Big Bang suggests that protogalaxies must have grown in the so-called Dark Ages. As of May 5, 2015, The galaxy Edes 1 is the most distant and earliest galaxy measured, forming 670 million years after the Big Bang. The light from Edes 1 has taken 13 billion years to reach Earth and is now 30 billion light years away because of the expansion of the universe during 13 billion years. On 17 August 2022, NASA released a large mosaic image of 690 individual frames taken by the near-infrared camera NIRCam on the James Webb Space Telescope JWST of numerous very early galaxies. Some early galaxies observed by JWST, like Cirrus 93316, a candidate high-redshift galaxy, has an estimated redshift of approximately Z equals 16.7, corresponding to 235.8 million years after the Big Bang. The detailed process by which the earliest galaxies formed is an open question in astrophysics. Theories can be divided into two categories, top-down and bottom-up. In top-down correlations, such as the Eden-Linden-Bell-Sandage ALS model, protogalaxies form in a large scale, simultaneous collapse lasting about 100 million years. In bottom-up theories such as the Searle-Zinnes model, small structures such as globular clusters form first, and then a number of such bodies accrete to form a larger galaxy. Once protogalaxies began to form and contract, the first halo stars called population Roman III stars appeared within them. These were composed almost entirely of hydrogen and helium and may have been more massive than 100 times the Sun's mass. If so, these huge stars would have quickly consumed their supply of fuel and became supernovae, releasing heavy elements into the interstellar medium. This first generation of stars reionized the surrounding neutral hydrogen, creating expanding bubbles of space through which light could readily travel. In June 2015, astronomers reported evidence for population Roman III stars in the cosmos redshift 7 galaxy at Z equals 6.60. Such stars are likely to have existed in the very early universe, i.e., at high redshift, and may have started the production of chemical elements heavier than hydrogen that are needed for the later formation of planets and life as we know it. Evolution. Within a billion years of a galaxy's formation, key structures begin to appear. Globular clusters, the central supermassive black hole, and a galactic bulge of metal-poor population Roman II stars form. The creation of a supermassive black hole appears to play a key role in actively regulating the growth of galaxies by limiting the total amount of additional matter added. During this early epoch, galaxies undergo a major burst of star formation. During the following 2 billion years, the accumulated matter settles into a galactic disk. A galaxy will continue to absorb infalling material from high-velocity clouds and dwarf galaxies throughout its life. This matter is mostly hydrogen and helium. The cycle of stellar birth and death slowly increases the abundance of heavy elements, eventually allowing the formation of planets. The evolution of galaxies can be significantly affected by interactions and collisions. Mergers of galaxies were common during the early epoch, and the majority of galaxies were peculiar in morphology. Given the distances between the stars, the great majority of stellar systems in colliding galaxies will be unaffected. However, gravitational stripping of the interstellar gas and dust that makes up the spiral arms produces a long train of stars known as tidal tails. Examples of these formations can be seen in NGC 4000, 676, or the Antennae galaxies. The Milky Way galaxy and the nearby Andromeda galaxy are moving toward each other at about 130 km/s, and depending upon the lateral movements, the two might collide in about 5 to 6 billion years. Although the Milky Way has never collided with a galaxy as large as Andromeda before, evidence of past collisions of the Milky Way with smaller dwarf galaxies is increasing. Such large-scale interactions are rare. As time passes, mergers of two systems of equal size become less common. Most bright galaxies have remained fundamentally unchanged for the last few billion years, and the net rate of star formation probably also peaked about 10 billion years ago. Future trends. Spiral galaxies, like the Milky Way, produce new generations of stars as long as they have dense molecular clouds of interstellar hydrogen in their spiral arms. Elliptical galaxies are largely devoid of this gas, and so form few new stars. The supply of star-forming material is finite once stars have converted the available supply of hydrogen into heavier elements. New star formation will come to an end. The current era of star formation is expected to continue for up to 100 billion years, and then the stellar age will wind down after about 10 trillion to 100 trillion years, 1014 years, as the smallest, longest-lived stars in the visible universe, tiny red dwarfs, begin to fade. At the end of the stellar age, galaxies will be composed of compact objects, brown dwarfs, white dwarfs that are cooling or cold black dwarfs, neutron stars, and black holes. Eventually, as a result of gravitational relaxation, all stars will either fall into central supermassive black holes or be flown into intergalactic space as a result of collisions. Larger scale structures. Deep sky surveys show that galaxies are often found in groups and clusters. Solitary galaxies that have not significantly interacted with other galaxies of comparable mass in the past billion years are relatively scarce. Only about 5% of the galaxies surveyed are truly isolated, however. They may have interacted and even merged with other galaxies in the past and may still be orbited by smaller satellite galaxies. Isolated galaxies can produce stars at a higher rate than normal, as their gas is not being stripped by other nearby galaxies. On the largest scale, the universe is continually expanding, resulting in an average increase in the separation between individual galaxies. See Hubble's law. Associations of galaxies can overcome this expansion on a local scale through their mutual gravitational attraction. These associations formed early as clumps of dark matter pulled their respective galaxies together. Nearby groups later merged to form larger-scale clusters. This ongoing merging process, as well as an influx of infalling gas, heats the intergalactic gas in a cluster to very high temperatures of 30-100 millikelvins. About 70-80% of a cluster's mass is in the form of dark matter, with 10-30% consisting of this heated gas and the remaining few percent in the form of galaxies. Most galaxies are gravitationally bound to a number of other galaxies. These form a fractal-like hierarchical distribution of clustered structures, with the smallest such associations being termed groups. A group of galaxies is the most common type of galactic cluster. These formations contain the majority of galaxies as well as most of the baryonic mass in the universe. To remain gravitationally bound to such a group, each member galaxy must have a sufficiently low velocity to prevent it from escaping. See virial theorem. If there is insufficient kinetic energy, however, the group may evolve into a smaller number of galaxies through mergers. Clusters of galaxies consist of hundreds to thousands of galaxies bound together by gravity. Clusters of galaxies are often dominated by a single giant elliptical galaxy known as the brightest clustered galaxy, which, over time, tidally destroys its satellite galaxies and adds their mass to its own. Superclusters contain tens of thousands of galaxies, which are found in clusters, groups, and sometimes individually. At the supercluster scale, galaxies are arranged into sheets and filaments surrounding vast empty voids. Above this scale, the universe appears to be the same in all directions, isotropic and homogeneous. The Hercules Corona Borealis Great Wall Currently, the largest structure in the universe found so far is 10 billion light-years, 3 gigaparsecs in length. The Milky Way galaxy is a member of an association named the Local Group, a relatively small group of galaxies that has a diameter of approximately 1 megaparsec. The Milky Way and the Andromeda Galaxy are the two brightest galaxies within the group. Many of the other member galaxies are dwarf companions of these two. The Local Group itself is a part of a cloud-like structure within the Virgo supercluster, a large, extended structure of groups and clusters of galaxies centered on the Virgo cluster. And the Virgo supercluster itself is a part of the Pisces Cetus supercluster complex, a giant galaxy filament. Multi-wavelength observation. The peak radiation of most stars lies in the visible spectrum, so the observation of the stars that form galaxies has been a major component of optical astronomy. It is also a favorable portion of the spectrum for observing ionized H-Roman II regions and for examining the distribution of dusty arms. The dust present in the interstellar medium is opaque to visual light. It is more transparent to far infrared, which can be used to observe the interior regions of giant molecular clouds and galactic cores in great detail. Infrared is also used to observe distant, red-shifted galaxies that were formed much earlier. Water vapor and carbon dioxide absorb a number of useful portions of the infrared spectrum, so high-altitude or space-based telescopes are used for infrared astronomy. The first non-visual study of galaxies, particularly active galaxies, was made using radio frequencies. The Earth's atmosphere is nearly transparent to radio between 5 MHz and 30 GHz. The ionosphere blocks signals below this range. Large radio interferometers have been used to map the active jets emitted from active nuclei. Radio telescopes can also be used to observe neutral hydrogen via 21 cm radiation, including, potentially, the non-ionized matter in the early universe that later collapsed to form galaxies. Ultraviolet and X-ray telescopes can observe highly energetic galactic phenomena. Ultraviolet flares are sometimes observed when a star in a distant galaxy is torn apart from the tidal forces of a nearby black hole. The distribution of hot gas in galactic clusters can be mapped by X-rays. The existence of supermassive black holes at the cores of galaxies was confirmed through X-ray astronomy. Gallery.
Thank you for watching. Consider supporting the channel, leave a like and subscribe.